Well, let's continue with our examples from the previous video. All these are relations. We want to know if they're reflexive and or symmetric and or transitive. So the first one we'll look at now is a set of real numbers with the relation being less than or equal. Is it reflexive? Is if I choose the right numbers, if I choose 5 twice, 5 is less than or equal to 5. Actually, that's a great example. All we need is one number for reflexivity. Pick any arbitrary x in the real number, and x is less than or equal to itself. Of course it is. R stays. Is it symmetric? That's what I was thinking of just a minute ago. 5 is less than or equal to 5, but let's use 5 and 6. 5 is less than or equal to 6. Does that imply that 6 is also less than or equal to 5? Of course not. So the inequality less than or equal is not symmetric. The only way it would be symmetric is if you're taking the same number on both sides. But it has to be true for all two numbers you choose out of the real line. Is it transitive? Think of three numbers. If A is less than B, if A is less than or equal to B, and B is less than or equal to C, must it be the case that A is less than or equal to C? Of course it does. So transitive stays. Okay, slightly different. Let's see if anything changes. Our set is the real numbers. That means the double E, double R. The set is the real numbers and strict less than this time. I think it's going to be similar except for reflexive. 5 is not less than 5. So 5 does not relate to itself. It's not equivalent to itself. If A is less than B and B is less than C, does that mean A is less than C? Of course it does. So transitive stays. I tricked you and me. I went out of order. So we know it's transitive. But symmetry, you can't even find any pair of numbers that will work. If A is less than B, it is impossible that B is less than A. So symmetry fails. Okay, a little different this time. We're going to the set of integers. And the relation will be, they will be related if and only if the absolute value of one is equal to the absolute value of the other. So let's think about what that means. 5 is related to itself, but it's also related to negative 5, right? Because they have the same absolute value. Negative 5 and negative 5 relate, so they're equal to each other. I should say, if they're equal to each other, then they're related. If they're opposite of each other, meaning opposite signs, they're also related. So reflexive. Is the absolute value of A always equal to the absolute value of A? Sure is. So that stays. Symmetry. If the absolute value of A is equal to the absolute value of B, does that imply, for sure, that the absolute value of B is equal to the absolute value of A? Trivially. It's symmetric. Is it transitive? You get three numbers now, any three real numbers. If the absolute value of A is equal to the absolute value of B, and the absolute value of B is equal to the absolute value of C, does that mean the absolute value of A is equal to the absolute value of C? Sure. All three. Okay, this last example here is on R squared. So we're talking about ordered pairs of real numbers. XY is related to AB if and only if y minus 2x is equal to y minus 2b. Sorry, I said that backwards. Y minus 2x is equal to b minus 2a. Is it symmetric? Of course. Y minus 2x is equal to y minus 2x, no matter what. So reflexive is good. I hope I said reflexive before and not symmetric. I probably said symmetric. Well, it is reflexive. Now, symmetric. If this is equal to this, is this equal to that? Sure it is. And then transitivity. If y minus 2x is equal to b minus 2a, and b minus 2a is equal to c minus 2d, is y minus 2x equal to c minus 2d? Of course it is. So this is all three as well. And we'll find out later that equivalence relations that satisfy all three of those are special, and we'll spend quite a bit of time with them. All right, and we will return to this example in a little bit. Okay? The next definition. Okay, this is the way we write a relation where both members, both elements of the ordered pair come from the set A. And this is the relation. Let it be given, and just let A be any arbitrary, little a be any arbitrary element from capital A. If that relation is reflexive, symmetric, and transitive, I'll underline them, then this is an equivalence relation. It's got to be all three of them to be called an equivalence relation. And then we continue with this definition. In this case, and this is what I'm defining, the equivalence class of this single element is written like this. You just take that element and put the square brackets around it. It means not only does it contain A, this is a set, and it contains every element that is equivalent to A or related to A. Here a formal definition. This is the set of all B in capital A such that A is related to B. And obviously, since A is related to A is in this set. Okay, now we're going to go back and look at that example. We had xy is related to AB if and only if y minus 2x is equal to b minus 2a. So let's think about some things. I just said consider the entire equivalence class of the origin, 0, 0. Well, notice y minus 2x, this is like y minus 2x, 2 times x. When I plug in a 0, what do I get? That's equal to 0. Or are there any other ordered pairs that are going to give me a 0? Well, look at this one. Y minus 2x. It's different y's than x's, but 2 minus 2 times 1 also gives me 0. So if that's a 0 and that's a 0, that means these two things would be equal. So 0, 0 is related to, let's see what order we go, xy, 0, 0, 1, 2. And I got another one, another ordered pair, 5, 10. Because this is equal to 0. And we could come up with an infinite number of them. And I don't know if I've ever seen it like this, where you put this one relates to this, which relates to this, but I think that's valid. So if we were to graph it, 0, 0, and then 1, 2, I'm going to run out of, I'll draw really small here. 1, 2 we'll put right there. And then 5, 10 is going to be right about there. And if you notice, it's all linear. We could come up with an infinite number of points on this line. It happens to be the line that passes through the origin and has a slope that you might guess 2. let's maybe consider one more. So all of the points on that line in this relation, all of the points on that line are related to 0, 0. And they're all related to this, and they're all related to that. Let's consider one more. Let's take the equivalence class of 1, 1. Notice that 1, 1 would not be on that line, so we're going to get a different equivalence class. So this is going to, how about if I just say it contains an infinite number of points, but let's come up with a few of them. Well, it contains 1, 1 for sure, which is there. Let's see, we're doing y minus 2x. So that would be 1 minus 2 times 1. So that's going to give us a negative 1. What other ordered pairs would give us a negative 1? So let's pick, how about negative 1? How about, would 2, 5 give us a negative 1? 2 is the x value. No, 3, 2 comma 3. Because if x is a 2, this becomes a minus 4. 3 minus 4 gives us a negative 1. And what we'll find out is, 2 go up 3. We're going to have another straight line. And not only will it be a straight line, it's going to be another straight line with slope of 2 over 1. So the one we just did is going to look like this. So every line with that slope, I'm just going to, I should have used a different color there. Not a very good line there. But all parallel lines with this same slope of 2 are equivalence classes. So we have an infinite number of equivalence classes, but if you randomly pick a point on one of these lines, it is equivalent to, it's in the same equivalence class as every other point on that line. And it's not equivalent to any point off of the line.